Hello everybody, welcome and thank you so much for joining us. My name is Dan Browne. I'm a Professor of Physics at University College London and also a Strategic Advisor at Riverlane, and I will be chairing today's webinar. It's great to have so many people joining us. In the audience today we have a broad range of representatives from the quantum computing industry, including both software and hardware companies and academics from all around the world. So thank you all very much for being here. We're here to talk about what is arguably quantum computing's biggest challenge, quantum error correction. The purpose of this webinar is to dive deeper into this topic, discussing its current status and likely futures. We'll start by sharing some of the key findings from Riverlane's recently published quantum error correction report. Then we have plenty of time for questions from you, with answers from our panelists who I'll introduce shortly. Hopefully you will have already read the report, but if not, don't worry, you can download it for free at riverlane.com. Just head to the homepage and you'll find a link to the report on the main page. The URL is also on your screen now. But now let's introduce our speakers for today. We have Earl Campbell, Vice President of Quantum Science at Riverlane. Earl is a world expert in quantum error correction with nearly 2 decades of experience in fault-tolerant quantum computing architectures. Earl will be presenting the report headlines and will also participate in the panel later. Joining us in the Q&A session, we have 2 remote panelists, Nicolas Delfosse, Principal Researcher at IonQ, and Jérémie Guillaud, Chief of Theory at Alice & Bob. Unfortunately, Maria Maragcu from Riverlane could not join us today and sends her apologies. Starting with Nicolas, welcome. Would you like to take a moment to tell us a little bit more about yourself and your background in quantum error correction?
Thank you. I'm very glad to be here. My name is Nicolas. I've been working on quantum error correction for the past 15 years, since 2009 when I started my PhD. There's often stories of people who start being interested in a topic when they are 14 years old and they keep going in that direction. It's not my case. I ended up in quantum by pure luck. I was doing my master in number theory at this time, and Gilles Zemmour mentioned that he was looking for a PhD student to work on something quantum. That seemed very exciting to me, so I emailed him right away and walked as quick as possible to his office. I was convinced that other students were also interested in this topic and were on their way right now. So my PhD topic was quantum LDPC codes, which are very popular now. And after that, I spent some time in academia in different places, at École Polytechnique, at Sherbrooke University, at Caltech and UCR. And I spent 6 years at Microsoft. And about a year ago, I joined IonQ and I'm leading the quantum error correction team. I'm back to my PhD topic. We are investigating quantum LDPC codes in particular, and hopefully we're going to build it in a real machine.
Thank you very much, Nicolas, and welcome. We're also delighted to have Jérémie Guillaud from Alice & Bob joining us today. Welcome to you also, Jérémie. Can you also please tell us a little bit more about yourself and your work?
Thanks, Dan, and thanks to Riverlane for putting up this nice workshop. It's also my pleasure to be invited to join this panel today. Just like Nicolas, I arrived in quantum a bit by luck, a bit more recently, about 8 years ago when I started my PhD. I guess at this time the field was not what it was today, so some of us who arrived some years ago indeed arrived here a bit by chance. So I joined the team of Maziar Miraimi at Quantic in RIA Paris, and I started working on bosonic error correction, and more precisely on building an architecture for cat qubits. I really loved working on this during my PhD, and I had a feeling that this was a pure theory work. And then towards the end of my PhD, a startup was actually spin-off from our group, Alice & Bob. And so I joined to keep developing this architecture and actually making it a real machine in the world. So for the past 4 years, this is what I've been doing. I've been leading the theoretical research team at Alice & Bob that focuses both on quantum application, on architecture and theory and on modeling the devices and the hardware. And so just like Nicolas, I'm extremely excited to be in this field to actually bring those machines to life.
Thanks very much, Jérémie. Now for the key findings from the quantum error correction report. Over to you, Earl.
Okay. Thank you for the introduction, Dan. So I'm going to be presenting some of the key findings from the Quantum Error Correction Report 2024. So this is a report that Riverlane published in October this year in partnership with Resonance. So Resonance went out and conducted some desk research and some interviews with global experts in the field, including some of those that are joining us here today, in order to compile some of the data that was inside this report. So we're going to jump in and look at some of the key findings. So to start off with, qubit quality is incredibly important. So we need high quality physical qubits in order to enable quantum error correction and get even better logical qubits. And so what we're seeing here is just the progress of qubit quality over time. So on the y-axis here, we've got the best observed 2-qubit gate fidelity. And what we can see, and this is on a log scale, so we can see actually the progress is quite rapid over time. One of the things we can see is that there's no one particular qubit type that's massively outswinging from all of the rest. There's a general trend for all of these major qubit types towards getting better. And these best observed fidelities are around the 10 to the minus 3 mark. So this means that an error happens about 1 in 1,000 2-qubit gates for the best 2-qubit gate performance. And we've got a dashed line here highlighting what I like to call the practical QEC threshold at 10 to the minus 3 error rate. So we kind of think about this as being roughly the point at which you can implement quantum error correction and scale it up without a large overhead. Also important is what you might call the threshold or the theoretical threshold, which is a 1% chance of error. That's 10 to the minus 2. Most qubit types have long passed that point already. And once you reach the theoretical threshold, you can do proof of principle demonstrations, but the overhead of error correction is still going to be quite high. So you need to progress a bit further towards this practical threshold. Now, of course, there's a lot of subtlety here because these are the best 2-qubit fidelities that have been observed. And they might only be on a 2-qubit quantum computer. So what's important to also consider is what kind of 2-qubit gates you can get as you scale up to more qubits. So again, here are some results that are presented in the report. We've got some data. This is a snapshot in time, so recent processes from a variety of companies and different qubit types. And what we can see on the bottom axis now is the average 2-qubit gate fidelity. Not the best, the average across that processor. And then we're looking at only processors that have, say, 10 or more physical qubits. We can see that as you scale up to larger qubit counts, it does get a bit harder to maintain qubit fidelity. So 10 to the minus 2, there's a good chunk of processors that are able to achieve that between 10 to 100 physical qubits. But getting down to 10 to the minus 3 is more challenging. And part of the reason for that is that device fabrication becomes more important as you go up to larger and larger devices. And this is especially important for superconducting and silicon devices, making it harder for them to achieve consistently high fidelities at large qubit counts. But nonetheless, we have some fairly large processors here, comfortably below the theoretical threshold. This still doesn't capture everything because there are other metrics that go into whether you are QEC ready, whether you can demonstrate quantum error correction, such as how good your measurements are and whether you can perform them in the middle of a circuit. So in fact, the best way to see and measure whether a system is capable of executing quantum error correction is to actually demonstrate it. So in the report, we also survey a variety of achievements throughout the field in recent years, and I really do have to say I found the progress quite rapid in the last couple of years. So there's a lot of information here on this slide highlighting some of the key results. Too much for me to go through all of them. So instead, I'm just going to dive in and zoom into a couple of these references, and I'm going to link them back to that table that we saw on the previous slide. So here we are, we've gone back to the previous table, but we've just picked out one data point. And so this data point is an ion trap device made by Quantinuum. It has, I think, 56 physical qubits, if I remember correctly. And we see it's one of the devices that has the best the lowest kind of 2-qubit gate error rates that we surveyed in the report. And so we mentioned this in the context of what we call reference 13s. This was a brilliant demonstration where they showed how you can do small computations, preparing graph states using 12 logical qubits to protect it against errors. And this also built on a lot of previous publications from the Quantinuum team, where they showed break-even results, where their logical error rates were better, or on par at least, with the physical error rates. So that was an ion trap device. Let's look at another one of these data points, which is again one of the key references that we look at in the report. So this is now a superconducting device with 101 qubits made by Google. And we're citing here their key landmark result that came out this year, where they demonstrated well below threshold quantum error correction and scaling. So we can see they're comfortably below the theoretical threshold, but they also have a healthy number of qubits here, 101 qubits in this processor. What this enabled them to do was to look at larger and larger codes. So they looked at distance 3, 5, and 7 surface codes and observed that, yes, you do see the hallmark signature of quantum error correction, which is a clear trend of the logical performance getting better and better and better as you scale up to more and more qubits. And so this is a key result in the field, and what we'd like to see in the future is more of these dots moving upwards, maintaining these kinds of fidelities, perhaps improving them slightly, but taking them up to larger qubit counts. So another important set of challenges that are highlighted in the report are the processing challenges of QEC. So this is indeed something that is close to our heart at Riverlane. So when you want to perform quantum error correction, obviously the quality of the qubits and the quantity of the qubits is very important, but there's a lot that goes around this. And so in this figure here, we can see the processor at the bottom, and then there's this cycle where we take the error data that comes from performing quantum error correction on these qubits. It's passed to a decoder that then infers what the most likely error is, and some correction is decided upon and fed back into the quantum processor. So there's a lot of infrastructure here that's needed to support quantum error correction. And indeed, for quantum computing in general, if you go to a quantum computing facility or a laboratory, that what you'll indeed see is a room full of different components and infrastructure and electronics, and the processor is just a small part of this puzzle. So focusing again on the quantum error correction processing challenges, we need to figure out how to build more accurate decoders, highly accurate decoders that are getting better and better at determining the most likely error that was responsible for the error data. We need to do this fast and deterministically. So if we can't perform decoding fast, then quantum computers will slow down, and it's incredibly crucial that that doesn't happen. And then lastly, just the scale of the challenge, just the amount of data. So if we think about these applications that might need trillions of quantum operations, then a back-of-the-envelope estimate will tell you that this will generate about 100 terabytes per second of error data. So this is amongst the largest processing challenges that humanity tries to deal with. So these are big challenges that we have to try and solve to really scale up quantum error correction. And some of those references that I highlighted include progress in this direction at solving these problems. So now we're going to move on to talk about QEC codes, the approach to implementing quantum error correction. So Resonance went out and they conducted a comparison of the peer-reviewed research and what codes that were used in those pieces of peer-reviewed research over the last 15 years. And what we see in this pie chart is really quite a lot of dominance from the surface code, so around 2/3. So this is really the dominant and most mature approach to quantum error correction. But we also see as a healthy diversity of other approaches to quantum error correction, including topics like QLDPC codes and bosonic codes that some of our panel guests have already mentioned earlier today. But there's actually something more interesting when you look at the data in more detail. So this is just averaged across the last 15 years. We can also look at the trends over the last 15 years. And the first thing that should strike you here is that all the bars go up. So really the field has massively grown over the last 15 years. And this certainly chimes with my personal experience. But in addition to that, when we look at the details and see how each of the kind of families of codes have progressed, then what we can see is that although there has been a lot of QLDPC research in the past, it's only really been significant in terms of the volume of papers in the last 4 years. There's been a huge growth in QLDPC codes in the last 4 years. And we can see that since around the time that Jérémie actually started his PhD, as he mentioned, bosonic codes have been very much on the rise also. So these are some interesting trends, and it's going to be interesting to see over the next few years and to see if these two categories of codes continue to eat away at the dominance that is currently held by the surface code. So next, we're going to look at how different companies position themselves and implement quantum error correction. So again, Resonance went out and they profiled 29 different companies using a combination of desk research and interviews. And they asked them how far along in their journey towards quantum error correction are they. So I've kind of added some labels to this pie chart that comes in the report, giving you a guide from 0 to 4 in terms of their readiness levels. So the first key things to pick out, and maybe this is one of the surprises in the report that we'll talk about in the panel session, is that only 10% of companies said that they were not working on quantum error correction at all. The rest said that they were working on it in some form. Flipping over to the other extreme, the most QEC ready companies, these are the companies, 14% of the ones that replied to the survey, that saw quantum error correction as a differentiator for them. So these are companies where everything they do has quantum error correction embedded in their operations, and they really see that as something that differentiates them from other quantum computing companies. These typically have the most mature approaches to quantum error correction, and certainly internal teams. And then the rest of this pie chart has a kind of varying journey from stage 1 to 3, with the majority of it actually in stage 3. So we see that over half of the companies, even though they don't see it as a core part of their approach, are implementing quantum error correction as part of their broad strategy of developing use cases for the devices that they have built. So looking forward, what are the crucial problems in quantum error correction? Well, I highlighted just quantum processors, the quality and quantity, getting both of those things working at the same time will continue to be crucial in order to scale up quantum computing and quantum error correction. And also another interesting question is applications. What are we going to do with these error-corrected devices once they're built? I mean, ideally, we would have millions of physical qubits and able to support, say, trillions of quantum operations right away, but it's going to be a gradual process, and there's going to be an intermediate regime where we have devices on the scale of 1 million quantum operations. What should we use these devices for? One application that came back as being quite a popular domain, both through our surveys and our interviews with the global experts, was quantum chemistry. So thinking about the physics of quantum mechanical systems, essentially. We looked at the QOP as a metric and considered what metrics are important as we scale up quantum computers. And then lastly, again, close to our heart at Riverlane, the importance of classical electronics. So this is both on the decoding side, but also the control systems that enable quantum computing. There needs to be a huge scale-up effort, which initially is going to continue using FPGAs, but I think everyone is in agreement that in the long term, all of this classical electronic infrastructure will need to transition to an ASIC to enable larger scale quantum error correction. So that concludes the key findings from the report, and I'll hand over back to Dan to moderate the panel.
Thanks very much, Earl. Let's make ourselves a bit more comfortable as we turn to the Q&A. So please can we bring back our remote panelists, Nicolas and Jérémie, to join Earl. And to kick us off, I'd like to ask each of the panelists a quick question. From quantum error correcting codes to future metrics, as you've just seen from Earl, the report covered a lot of topics. But which results resonated with you particularly, and which maybe surprised you? Could we start with Jérémie?
Sure. I think one thing that really struck me when reading the report is the feeling that we are at the point in time where error correction really starts to work. When you think about it, the theory of quantum error correction was developed about 30 years ago with the early works from Daniel Gottesman, for instance, in the 19s. And right now we're really at a point where, and I think this was well shown in the graph where you see the quality of the quantum hardware over the years and you see the threshold, we're at the point where the hardware, the technology finally becomes good enough so that error correction can be done in practice. And I think a consequence of that, which is also very well shown in the report, is the fact that industry has really taken this subject. And now more than 90% of quantum computing companies are, actively pushing this effort. And so, yeah, very exciting times. And I think the report does a very good job at giving us this sense of history.
Thanks very much, Jérémie. Nicolas, did you have any highlights or surprises from the report?
Yeah, maybe I can mention two things. So the first high-level thing that comes to my mind is the scope of the problem. You mentioned in the report building ASICs for decoding or FPGA for decoding, building different types of quantum error correction code, or even application to the electronic problem simulation. And this is a massive problem. We need expertise from very different fields, from engineering, computer science, math, chemistry, computer architecture, and we need more cross-discipline communication, more communication with our neighbors to make it work. It's impossible without that. We need to communicate more. And the second thing I wanted to mention is I like your classification of quantum error correction code very much. Like the surface code is the safe bet, quantum LDPC code, high risk, high reward. And I'm also expecting some surprises. There is a lot of great work that is not as popular, but that will maybe become more and more trendy over the next few years, like concatenated code, that the work of Yamakasi and Kohashi is bringing back. And there is a lot of more exciting work outside of that will maybe also become serious candidates.
Thanks very much, Nicolas. Oh, do you have anything to add?
Yeah, I think I'll also pick on the pie chart where we only had 10% of respondents saying that they weren't pursuing quantum error correction at all. And to try and put that in a bit of context, certainly at Riverlane, we've been going out talking to companies about helping them with quantum error correction. And anecdotally, at least, what we've seen is a lot more people saying, yes, please, over the last year. And a year ago, there were quite a few people saying, not right now, we're good with NISC, for example. So it was an interesting piece of snapshot data. I'd be really curious to see what that pie chart looked like 3 years ago. And yeah, also maybe even what it would look like next year.
Thanks, Earl. So now let's turn to your questions. And it's an interesting question on metrics. So these were mentioned in Earl's talk. And the question is, what metrics do you think we need to compare quantum computers? And what metrics do you use in your company? Who would like to start?
I can start. So I think in terms of, I think metrics that are important for NISC hardware and error-corrected hardware are really different. So we've been using the past couple of years of metrics such as quantum volume, which really well capture the volume, as the name suggests, that a certain hardware can execute. So it captures both the number of qubits that is available, the fidelities of the gates that are available, and so roughly the kind of quantum computation that you can do with this kind of hardware. I don't think it's very well suited for error-corrected devices, because you can really argue that when you are above threshold, the volume might not be impressive at all. And then there is really a threshold effect where if you're below threshold, then in theory, you can increase the quantum volume to infinity by just increasing the code distance. So I think for error-corrected devices, there are two main metrics that really matter. There is this so-called lambda factor, which captures how far below threshold you are. And that metric really matters in the short term because it really shows which technology is able to be operated below its threshold, with, for instance, superconducting circuits being at a lambda of about 2 for surface code right now in the last experiment by Google put on the archive in September. And the other metric that really matters in the long term, perhaps the only metric that matters in the long term, in my view, is the so-called teracorp footprint, meaning what is the overhead, what is the size of the quantum computer that you need to build to run reliably 10 to the power 12 quantum operations. And so this metric alone aggregates a lot of things that are extremely important, such as the efficiency of our quantum error correcting scheme, how far below threshold you are operating, and basically it melts down all of the things that really matter for a quantum error corrected quantum computer.
Thanks very much, Jérémie. So that was a pretty comprehensive answer from Jérémie, but Nicolas, Earl, would you like to add anything?
Yeah, I can add that as I kind of highlighted in presenting some of the results from the report, there are lots of metrics like 2-qubit gate fidelity and say measurement error and such what that individually give you an incomplete picture of what's going on. So actually one kind of composite metric of all of those things is what kind of logical fidelity can you achieve? How good is a logical qubit that you can build out of all of those components? And so one of the things that we mentioned in the report is the idea of the QOP. So what is a QOP? Well, really, it's just 1 over the logical fidelity, right? It's just saying, roughly speaking, how many logical operations could you perform? And it's very similar to, in some sense, the lambda parameter that Jerry mentioned. That's kind of like the rate at which you achieve QOPs as you scale up. One thing that kind of QOPs covers that lambda doesn't is, if you gave to me a device that had, lambda equals 10, and it had 100 physical qubits, but as soon as you went to 200 physical qubits, lambda got worse, then that doesn't necessarily give you the full picture. So somehow you also need to try and capture quantity as well as quality. And also looking at some metric like QOPs will do that, although I realize that it's also not a complete picture.
Thanks very much, Earl. So now let's move to the next question, which considers how we might use these metrics. And the question is, at what stage can quantum error correction be considered to have been achieved? So when has the job been done? Since increasing the code distance can lead to an arbitrarily low error rate, what is a good stopping point for declaring QEC successful? So Nicolas, would you like to comment on this?
Yeah, it's actually very related to the previous question. To me, the main issue is that we don't have the killer app for a quantum computer yet. And when we're asking that, when are we done? When do we have enough QEC? The answer depends on what you're going to do with your machine. So for instance, if you are watching TV, there is some error correction that is running there. But if you see that a few pixels are flipped during one of the images that is broadcast on TV, you are not even going to notice it. You can afford a fairly high noise rate. If you are sending a picture from a space probe that costs $1 billion to send there, you don't want to have a pixel that's incorrect. You need much more reliable error correction. So it depends on your application. And it's a hard question to answer because we don't know the killer app yet.
Thanks very much, Nicolas. Would anyone else like to add something to that? What is our finish line in the QEC race?
I can perhaps say what is not the finish line. I just want to point out the fact that you may think that achieving a lambda factor well above 1 would mean that now it's just a scaling problem. But as Earl was just suggesting, we do know that when we scale a quantum processor, it's very hard to maintain its quality. So the lambda factor might decrease as you scale up. And I should also mention that from a theoretical perspective, the community is really focused on the threshold, the value below which the value of the physical noise below which error correction works. But we do know that there is something else that's important, is the fact that the noise that you have in your system actually obeys the hypothesis that you made for error correction. So now that we enter the regime of error-corrected device, we see those phenomenon where you start suppressing the logical error with quantum error correction up until you saturate to some logical floor, because there you hit a physical error mechanism which is not satisfying the hypothesis of quantum error correction, such as, for instance, the fact that the noise should be independent on the qubit. So with this in mind, I think we will never be really sure that error correction is a solved problem up until we've demonstrated experimentally that we can build logical qubits at the rate, at the error rate at which they need to be for the actual application.
Now moving on to another question, which really is about what has happened in this year, in 2024. And the question is, what has been the standout moment in QEC for you over the last year? Oof. Who would like to take that? I mean, Earl, you already mentioned several highlights in your presentation.
Yeah.
Nicolas, Jérémie?
Yeah, I'm happy to start with that one. I will mention 2 of them, one experimental, one theoretical. So the experimental one to me is the Google surface code experiment. It's a great breakthrough. Until recently, we still had some skeptics in the community thinking that maybe noise is too correlated. We cannot build a machine where there is little correlation, and error correction does not work well with correlations. So we could have imagined that it's just impossible. And it's not that crazy when you think that physics is non-local. So today we can see with this experiment that they can even reach 10 to the minus 10 in logical error rate for the repetition code. It's not useful in practice, but it's a great experiment and a proof of principle that QEC does work. And on the theoretical side, I like the work on magic state distillation very much. That proves recently that in theory, asymptotically, we can do magic state distillation in constant overhead. It's a great theoretical breakthrough. It's not practical yet, but I'm sure it's going to keep leading to further work to improve, reduce the cost of fault-tolerant quantum computing, and every such improvement brings us closer to large-scale applications.
Thank you, Nicolas. Jérémie.
So just like Nicolas, my favorite was Google Superscode experiment up until the experiment by AWS on cat qubits. So let me comment why. I think by any means the experiment by Google is the most impressive quantum error correction experiment that we've seen in the field so far. Yet I think the fact that AWS was able to build a logical qubit using cat qubits in a repetition code, which is a much more recent architecture, which is much less mature, both from a theory perspective and also from an experimental perspective. So if you think of the amount of resources and time that have been invested into both technologies over the past few years, then you will realize that really cat qubits are a newcomer, and a lot of things that are now well understood and well settled about transmon, such as the regime in which they should be operated, result from a decade or even more of brute force engineering, which allowed Google to demonstrate the surface code that they have. So yet I'm a bit more excited about that result with AWS, because I think when you look at those error correction results, you should always bear in mind, what was the effort that was really invested to get there, and does it tell you something about how good is this approach fundamentally? If you can achieve something similar with much less resources or much less maturity, it probably means that it's fundamentally easier. So disclaimer, I work for Alice & Bob that's pursuing a very similar technology as AWS. So I know I'm biased in the appreciation of that result, but I just wanted to mention that now it's really this result that is the most impressive for me.
I think we had some good coverage, especially of the experimental side of results, but we missed out neutral atoms. And I think if we're talking about results of the last year, we've definitely got to give a shout out to the Harvard experiment that really, I think, surprised a lot of people in terms of how quickly the underpinning technology in neutral atoms had leaped forward. They had gone from a place where there were essentially no error correction experiments at all to one where they had, multiple impressive results in a single paper. Each of those individually could have been a breakthrough result in its own right. I think that surprised a lot of people.
Thanks, Earl. So now the next question moves to applications. So the question is, what are the current intentions for exploring applications of QEC to quantum physics and simulation? So I think what that's saying is, how will QEC enable quantum physics simulation beyond what we can do at the moment? Earl, would you like to answer that one?
I think one of the key things that I commented on towards the end of the summary of the report was how we're not going to suddenly leap forward where we have millions of physical qubits and trillions of quantum operations. There's definitely going to be an intermediate periods where we start doing first of all, we're doing some error-corrected computations, which people are already starting to do today with a few logical qubits that clearly don't demonstrate any advantage to quantum computing yet. The advantage is all in the scaling. And there's certainly going to be an intermediate phase where, just as we see already today around NISQ, there is an open discussion around has this been a demonstration of something that's a compelling example of quantum advantage or not. And certainly simulations of quantum mechanical systems is my favorite area to look for such demonstrations. And I think there will be a lot of the research on algorithms has bifurcated into two categories in the past. It's been very NISQ-heavy heuristics, where you don't have any guarantees and you do some numerics to see what the performance is. And then on the other hand, you've got a lot of very mathematically rigorous work that analyzes, assuming as many resources as you want, what you could execute, and arriving at these estimates like a trillion operations. And there's definitely something in the middle which is kind of underdeveloped at the moment, which is a focus on early error-corrected applications, where you allow yourself access to some heuristics, and you maybe use some techniques that work well pre-asymptotically but don't work well in the asymptotic regime. I think that's definitely an under-researched area that I'm looking forward to people exploring more in the next few years.
Thanks, Earl. So let's move on to a question about what QEC means for quantum computing companies. So specifically, what QEC challenges do quantum computing companies face as they approach fault tolerance? Who would like to go first?
Okay, maybe I'll comment on the one which has kind of surprised me more in recent years. So I already knew about many challenges, the challenges of decoding, the challenges of qubit quality, quantity, etc., etc. But the thing that I've learned in the last couple of years is just how complex classical electronics are, both not just on the decoding side, but also on the control side. So scaling up control systems, but also integrating them with other systems to work in real time is actually a much bigger problem than I had previously realized. And also doing that in such a way that you have, modest power consumption and the components aren't too expensive. There's a lot of work to be done in that area. In addition to all of the other problems that I was kind of already more aware of, this has been the one that's surprised me in the last couple of years.
Thanks, sir. Jérémie, I think you had something to add.
Yeah. What I was about to say is that I think, the elephant in the room is still that it's extremely challenging to make error correction work, even though, the progress in the past few years and the now experiments that are below threshold give us all a lot of optimism for the next few years. It's already extremely challenging to be at threshold, as we mentioned, and as Earl explained in the introduction, where we want to be is rather at least an order of magnitude below threshold, so that resources needed by error correction are not completely unreasonable. And I think what we've seen in the very recent years with people actually now implementing error correction is more and more noise awareness in theoretical constructions. I think still a couple of years ago, like the noise models assumed by theorists in really researching high-level error correction were a bit naive with respect to what we have in the lab. And now that there are a lot of people actually building the systems, there is really something feeding the theorists, which is the actual fine-grained structure of the noise. So for instance, one example in the recent few years is those erasure qubits that have realizations both with neutral atoms and in superconducting qubits, where people have really realized, are really looking in details what are the actual error mechanisms in the lab, and then try to think of error correction strategy that are tailored to such a refined error model. And that's really something that that is now both a blessing and a challenge for people actually building the hardware is really refining those error correction strategies to make sure you can actually go well below threshold.
Thanks very much, Jérémie. Nicolas, did you have anything further to add on that?
To my view, one of the main challenges is the same that we face in the whole community. It's communication. When you are working on quantum error correction, my team at IonQ is supposed to work with people building qubits, building a trap, and people working on the architecture of the machine, on applications. All these people are very specialized in their own area, and it makes communication very hard. They sometimes don't know what is error correction, how it works, what is the cost of error correction, and we need to break these barriers. It's a lot of work. My personal experience, the first time I was really facing that was a few years ago when I worked with an intern coming from computer architecture. And I realized I don't have the language to chat with her. It was Poulami Das. Now she's a professor at UT Austin. and there is some problem that we cannot solve without combining expertise from two different fields. And sometimes we don't even know that we have the joint expertise to solve this crucial problem. So we need more communication between different fields, with the adjacent teams, and it's very beneficial. If you are a PhD student, you want to work with people in a different field, do it. It's very beneficial. The first benefit is that they believe you are really smart, because you bring all the ideas of your community to them, and they believe it comes from you, that you're amazing. It's not the case, but it's very easy to look smart when you come with different ideas. And we need to solve this problem together.
Thanks very much, Nicolas. So on the topic of working on this problem together, all three of you lead teams of quantum error correction researchers and developers. And I guess you have thought very much about how you grow your teams. And a relevant question is from Alexander Berezutsky, who asks, I currently work on tensor network decoding in my PhD. My background is in physics. What would be the best way to transition into quantum error correction? So what's the best way, if your background is in physics, how can you get into quantum error correction? Would anyone like to?
Well, my background was in physics. I think many of us actually had a background. Many of us had a background that was in physics. So I think it can be quite natural to transition. I think now there are a lot more opportunities than there used to be. Certainly when I did my PhD, there was no such thing as an internship at a quantum computing company. And many people now, when they do a PhD, will do an internship. So I think that's definitely a good route to diversify your understanding of the field if you choose the right one. There are some great summer schools that I think PhD students could attend that focus just on quantum error correction. And if you go to one of these events, you should just talk to other people, talk to as many people as you possibly can, try to understand what they work on, and then build out your network and your collaborations.
Thanks, Earl. Jérémie, Nicolas? I mean, I guess, we could maybe broaden the question a little bit to, if somebody is interested in moving into quantum error correction from outside of this field, maybe from a maths background or computer science background, what would be the best first steps for them to take?
I mean, I think so far there is no such thing as a quantum error correction background, or perhaps very recently with a lot of universities that are starting to put up real quantum programs. But I think all of the people who are currently in the field actually come with a different background, whether it be mathematics or physics or even computer science. And I think quantum error correction in itself, as Nicolas was mentioning, is a very complex problem that requires a lot of different expertise. Even in the field of quantum error corrections, you have very math-oriented people like Nicolas, actually, who do, like really theoretical work, but you also have a much more applied and numerical research. For instance, one of the most famous researchers in our field is Craig Guinet from Google. He was a software engineer at Google, and then actually started working on those on the surface code, not on very abstract and theoretical codes, and really became a reference and solved many practical problems that we have. And I could cite other examples. So I think for somebody who has a background in physics and who knows about tensor network decoding, it's already an impressive toolkit to jump into the field. So as Earl mentioned, I think a lot of quantum companies would be happy to recruit such profiles and put them in an error correction team.
Thank you, Jérémie. Nicolas, do you have anything to add?
Yeah, I agree that tensor networks are, in this special case, tensor networks are extremely useful. At some point, we need to do some very accurate simulations of error correction schemes, and one way to do that is to use those tensor networks. So it makes a lot of sense, but more generally, my advice for someone who wants to move to error correction is usually that they should look at the literature, find papers or researchers that they like their work, pick their favorite paper and try to reproduce the result, make a numerical simulation, see if they can understand all the details, and after they should reach out to them and to ask them if they are hiring, if they are if they have some recommendation, and they will already see by reproducing the result, by doing a simulation, if they like working in this field. They will learn a lot, and it's going to be a useful first step.
Thanks very much, Nicolas. So now I'm going to switch to some questions on hardware. And the first of these is on a topic very close to my heart. What is the current stand of photonic quantum computing? It wasn't compared in the report. Would anyone like to comment on that?
That's a tough question for the audience here, I think. I mean, a disclaimer, I'm not an expert in photonics architecture. I think there has been a lot of progress in this field recently. There is a nice overview paper by PsyQuantum really summarizing, what are the key obstacles to overcome and makes a nice overview of the recent progress in overcoming those. But yeah, I cannot really give you more insights than just pointing to this reference.
I think it was mentioned in the context of MBQC codes and the survey of what different papers had been looked at. The tricky thing with photonics for me is that with a lot of different qubit types, you can just say, here are the number of qubits. With photonics, it's not really correct to compare the number of photons to the number of qubits. So when you work in one of these MBQC models, usually you'll start off with something like a resource state generator that has like 6 photons, and the idea is that you fuse them together to make a graph state with fewer qubits that are used for error correction. And so the number of photons is not in one-to-one correspondence with the number of qubits that would be used for error correction. And additionally, also to do error correction, you need to generate either large graph states or semi-deterministic entangling gates. The majority of photonic systems out there at the moment are, say, boson sampler machines that don't have deterministic interactions. And as a consequence of that, there are no QEC experiments using photonics today. So whilst there are a lot of promising prospects in terms of some of the scaling challenges are different for photonics, so if you can overcome these problems, maybe they will move faster. So there is an argument in that direction. If you try and take a snapshot of where QEC is today in photonics, it's strongest in the theory papers, really. The actual demonstrations are not there today. That's why I would imagine there's less of it in the report.
Thanks, Earl. And it's certainly true that the leading photonics companies like PsyQuantum and Xanadu have really put quantum error correction right at the heart of their strategies for scaling up. Let's move now more broadly, thinking about different hardware platforms and how they might work together. So here's a question from Jacob Fong, which asks, what are your thoughts on the feasibility of linking different qubit modalities into a single system to leverage different system advantages? What would be the impact on quantum error correction? So could there be some advantage in error correction from combining different types of hardware?
So maybe I can mention 2 things. So the first one would be first combine the same type of hardware, combine 2 QPU built with the same qubits. This is a very viable approach. It's actually the approach that IonQ is pursuing. Build small modules, high quality small modules, and connect them, in our case, with optical interconnect. This is a strategy proposed about 10 years ago in this music architecture paper. It's a viable approach because it's modular, it's simple. You build a small module and you replicate it many times. And we can imagine doing the same thing with different qubit modality when it's possible to connect them. It may require some conversion in optics that are challenging. It's not that simple, but just like we have a classical computer with different type of memories and different type of hardware to store information, we may benefit from that.
Earl, Jérémie, do you have anything to add?
Yeah, I guess I agree. The most obvious one would be distributed networks where you have a mixture of optical and matter qubits. I mean, other examples might be if you were to try and combine, let's say, something like superconducting qubits where you have fast gate times but short coherence times with something like neutral atoms or ion traps, where you have longer lifetimes, and you might try and use, say, one of them as a storage and one as a processor. So there are some kind of natural things, but I think for all of these ideas, as you were saying, Nicolas, there's often, at least in optics, there's literal photon loss at the interface. When you go from kind of one mode to another mode, you have a lot of loss. And I think one of the reasons we don't see lots of hybrid architectures is that one of the things we're really trying to solve at the moment is how do you improve the quality of qubits? When you then say, I want two different qubits that are completely different, have different natural frequencies that they might work at, and get them to interact, it becomes even harder to achieve those high fidelity operations. So there's always an extra challenge at the interface of two technologies.
Thanks, Earl. Okay, so our time has flown, so this will be our final question. And at the beginning of this discussion, we talked about our highlights from the last 12 months. So now looking forward to the next 12 months, what do you think we'll see in error correction over the next year? Who would like to go first? Who can gaze into their crystal ball and have the clearest vision?
Okay, I'm going to make a pessimistic bet because we are too optimistic. So, you know, we have been through NISQ. NISQ was very trendy. People were maybe over-optimistic. We still don't know if there is anything there, but the community, the core of the quantum community is moving to QEC clearly, as we see in your report. And my bet is that we are not in the QEC era yet. We still need a lot of work. It may feel like that, but QEC is not useful yet. And we are going to see more interesting results, maybe without error correction or with very little error correction. And the community is going to realize more and more that we need a few years to have QEC working for practical applications.
Thank you, Nicolas. Jérémie, what do you see in the next 12 months?
I'll be on the optimistic side. I mean, I think right now we're at the point where, thanks to error correction, we see quantum memories, so just a single logical qubit preserved in time. I'm really looking forward to having like a small fault-tolerant quantum computer on its own. So really a quantum computer that, thanks to error correction, demonstrates both a few logical qubits, but also logical gates between those qubits, and a universal set of logical operations. So for instance, a small magic-state distillation factory or things like that. I would really love to be at this point where we can safely say now it's just about scaling this hardware. And I think we still have a lot of work to get done to get there. But given the fast progress in the next couple of years, I'm optimistic that we'll see that in just the next few years.
Thank you, Jérémie. Oh,
I've got a few on my shopping list. I'm going to go for, I think we'll see a pretty good QLDPC code demonstration in neutral atoms. I'd be surprised if that doesn't happen over the next year. It'll have some limitations. Most likely we'll only do one round of error correction. We might see something like a modest size like the 144 data qubit bivariate bicycle code. I think in superconducting qubits, I'd be really keen to see if these ideas that came from the Google team on the hardware-aware surface code, the one that uses the I-swap gate, result in big improvements in lambda. So I would like to see that, and maybe, even try and help it happen. And then lastly, also something I'd like to help happen is just a lot more progress on the real-time decoding side. So I think we've had some impressive results, and we've seen demonstrations, usually assuming toy noise models of memory experiments, but just a broad diversification. There's lots of other experiments have already been done using offline decoders, but just to do all of that work with real-time systems, really digging into specifics of noise models that are tailored to different qubit types, and even supporting things like logic and teleportation. It's going to be exciting.
Thanks very much. Thank you. Thanks, Nicolas. So that brings us to the end of our discussion. Thank you to all of our panelists for a fantastic discussion, and to everyone who's joined us online. As the end of 2024 fast approaches and progress in QEC continues to accelerate, the team at Riverlane are already thinking about what to put in the Quantum Error Correction Report 2025. So if you'd like to share some suggestions, or are interested in featuring as a contributor, as Jérémie, Nicolas and myself did, you can get in touch by emailing media@riverlane.com. Personally, I'm excited to see what breakthroughs will be made in quantum error correction. As we've heard, it's evolving quickly, and I'll be fascinated to see where we are a year from now. Thank you very much, and goodbye.